This is to help us become more familiar with using Gauss's law, specifically in a problem with spherical symmetry. So first, we'll start by simply writing down what Gauss's law is. Gauss's law says the electric flux equals the charge enclosed divided by the permittivity of free space. Now, the permittivity of free space we've already talked about. It's a fundamental constant of nature, so we just know its value is permittivity of free space is 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. So that's a fundamental constant, not a big deal there. What is the flux? The flux is a way to measure how much electric field is going into or out of an enclosed region. So quite technically, the flux is defined by an integral. That is, the flux is equal to the surface, the integral over a closed surface. That circle means over a closed surface. Integral is just a way of saying summation over every tiny piece of the electric field vector dotted to each tiny little piece of area. Now, of course, if you're not in the calculus space class, you can't use that equation because you don't know how to do an integral. But the ideas can be written in algebra form. It's the summation over closed surface of the electric field parallel to the area for each piece of that closed surface. So for instance, if you have a cube, you would take each surface of the cube, so you'd have a total of 6 different pieces to the summation, the electric field for each surface dotted to the area. Remember, the dot product means the parallel parts. So we can go a step further. Since it's the parallel parts, we can replace the dot product with the magnitude of the electric field times the magnitude of the area times cosine of the angle between the area and the electric field. Now, most people, when I say the direction of the area, they're at best confused. If I have a surface, so here's a surface. If I want to know what direction the area points, the standard used in physics is that the area is in the normal. Well, I should have put in the direction normal too. Let me fix that. To the surface. Now, I have noticed that our textbook actually replaces the word normal with the word perpendicular. Technically, that's not an appropriate change, but that's what our textbook does. It does that because to find the normal, you just take every possible line that you could draw in that plane, and you find the direction that is perpendicular to all of those lines and coming out of the surface. So the thing that's perpendicular to all those and coming out is going like this. So that's the direction for the area of a surface. Or if you are looking at a flat piece of paper coming directly out of that paper toward you, coming up out of the floor, that's the normal direction, just like we used with normal force. So, the angle cosine, or the angle theta in here is the angle between the area to the surface and the electric field. So there's where our angle theta would be. So you have to sum the electric field times the area times cosine of the angle between the area and the electric field for each piece of the surface. Now, in calculus class, you can do this if the electric field is varying over the area. For algebra-based, you really can't do it unless you have a constant electric field over the surface of the area, or, so you need electric field is constant over area, or the electric field is perpendicular to the area. If the electric field is perpendicular to the area, then E dot A equals EA cosine theta is just equal to 0. So there's no flux for a surface if the electric field is perpendicular to the area. If the electric field is not perpendicular, then for calculus-based, we're going to need to have a constant electric field over the area and a constant angle between the electric field and the area. So that's what the flux part is. But the equation also had Q enclosed. What is Q enclosed? Well, the Q enclosed and the flux work together with this imaginary Gaussian surface. The Gaussian surface is not a real surface, but is a surface that you conjure up in your mind just to make calculations on. So it doesn't have to be physically there. A surface for calculational purposes. So you do your calculation of flux on this imaginary surface you make, and you calculate how much charge is enclosed by the same surface that you calculated the flux for. Remember, it needs to be a closed surface. It has to have no holes in it. So a sphere is an example with no holes in it. A cube is an example with no holes in it. A cylinder with caps on the top and bottom, no holes in it. Those are the shapes we usually use, we will always use, in a non-calculus based class to match the situation at hand. Now, in this lesson, I'm going to specifically look at spherical symmetry. I'm going to look at charge that's distributed in a cylindrically symmetric fashion. So I have a symmetry that's going to allow me to have the electric field is only dependent on how far away from the center of the circle you are, and the direction of the electric field will always be parallel to the area if you use a spherical shell. So I'll use a spherical shell to match the symmetry. The electric field then will be constant over an area with constant radius, and the angle between the area and the electric field will always be 0 degrees. So let's go to looking at a problem. So here's a problem. A solid conducting sphere that carries a total charge of minus 16 microcoulombs. My red circle here is a flat cutoff view of the center sphere. Is placed at the center of a hollow conducting spherical shell that carries a total charge of 8 microcoulombs. Notice it's a positive charge in the exterior one, a negative charge in the interior one. The conductors are in an electrostatic equilibrium. That means that nothing's moving around, they're just sitting there stationary. We have strings attached or something to hold them in these positions. And then our job is to determine the charge on the outer and inner surfaces of the shell and sketch a field line diagram. So to do this, well, there's many ways to try to do it, but the easiest way is with Gauss's law. So let's start in the center of the circle. So I'm going to take a Gaussian surface. Let me make a green Gaussian surface here. And this Gaussian surface is going to be a sphere with a radius smaller than the radius of the inner shell. So if I make this sphere that's smaller than the radius of the inner shell, I can then apply Gauss's law to it. So I'm going to have Sorry about that. Flux inside is equal to the sum of the electric field, well, let's do it this way, electric field times area times cosine theta over the surface of that green spherical shell. Very simple question. What is the direction for the electric field if it exists in here? Well, it's going to have to be radial. Given our symmetry, the electric field has to be going either directly in or out of the charge. So my area for this surface is going out, and the electric field is going in or out, so the angle between them has to be 0 degrees. So theta equals 0 degrees, therefore cosine of 0 degrees equals 1. And then I just have the sum of the electric field times the area. What's the area for the sphere? The area of a sphere is 4 pi r squared. The electric field, I'll just put E inside. So there's the flux part. Now, of course, that's equal to the charge enclosed over epsilon 0. Now, there are two ways that I can go about this because you know the answer to both of these questions. Question number 1, what's the electric field inside a conductor? Question number 2, what is the net charge inside a conductor? Both of those answers are 0. We learned that the net charge is always distributed on the surface of a conductor. So the net charge inside is 0, the electric field inside is 0. Those have to go together. So we have electric field inside, or just ions, is equal to 0. The charge enclosed is equal to 0. Well, that was trivially easy. Would that it was that much easier always. So if the charge is all on the surface, then I can answer my first question. The charge on the outer surface of the inner ball, which I will just call Q1, has to be the entire charge in that ball. So I'm going to end up with Q1 is equal to Q on the inner ball, which is equal to minus 16 microcoulombs. Now that I have that, let us consider, this is not actually part of the solution for the problem, but let us consider, got to go back to the circle. Let's consider the electric field out here where this magenta line is. This magenta line is between the inner ball and the outer ball. Now, according to Coulomb or Gauss's law, all that matters is the charge enclosed. So if I go through and I do Gauss's law again, wow, that's 2 in a row. I'm going to avoid that next time. Okay, that looks exactly like what I wrote above. And indeed, the area is still going to be 4 pi r squared, and the cosine theta is going to be 1. So that's just going to be the electric field. Actually, I should have called it middle or mid rather than center, because center sounds like it's at the center of the whole shooting match. Mid is midway out, okay? So that's E mid times 4 pi epsilon 0. And that's equal to the charge enclosed over epsilon 0. Well, now the charge enclosed by this magenta sphere is the entire minus 16 microcoulombs. There's no epsilon 0 here. That's an r squared. Now let's solve this for the electric field. Now this is kind of mixed. I have the charge in the actual number, and I have everything else in symbols. If you look at this equation, it should look familiar to you. This is, remember, K is 1 over 4 pi epsilon 0. So this is the same as saying this equal to minus 16 microcoulombs, which is the charge enclosed, over r squared times k. Oh man. Now remember, the three lines simply means is defined as. K is defined as 1 over 4 pi epsilon 0. So this is what we get from Coulomb's law. So it's in agreement with Coulomb's law. What does that minus sign mean? Well, it means the electric field is going inward in this case. So the electric field in the center part has to be pointing, and I will draw a few arrows with black in toward the center. And that makes perfect sense because we learned that electric field lines go into negative and out of positive. So now I've done a middle line. Now I'm going to do one that you probably didn't anticipate. That is, I am going to make a circle that comes out. Okay, well, you can see I didn't hit the center right on that. Let's try again and hope for the best. Well, that's better. I am sorry, my wife is calling. Okay, now let's use Gauss's law on that black circle. Now, once again, the black circle is completely within a conductor. What's the electric field inside a conductor? Well, it's 0. So when I use Gauss's law on this case, I have the flux. I really said I wasn't going to do that next time. The flux in the shell is equal to sum of the electric field in the shell times area cosine theta, but the flux in the shell is 0. That's equal to the charge enclosed over epsilon 0. Well, where could we have charge? Looking back at the figure, I had minus 16 microcoulombs here, and so if that's minus 16 coulombs and I have a total of 0 charge enclosed by this black shell, then that means the charge that is on the inside of the blue shell, blue shell, has to balance that out. So I have to have plus 16 microcoulombs there. Now, the last step I'm going to do is to say, well, what would the charge on the exterior of this be? I know that I have a total of 8 microcoulombs on this outer shell, and I have positive 16 on the inside. So how much is on the outside? Well, I'm going to have this 16 plus whatever's on the outside equals 8. Or solving it, 8 minus 16 is minus 8. So I have minus 8 microcoulombs on the outside of this shell. So now I've answered the question. I have minus 16 microcoulombs on the exterior of the inner sphere. I have plus 16 microcoulombs on the interior of the shell, and I have minus 8 microcoulombs on the exterior of the shell. So I was able to do this by utilizing Gauss's law.